everybody. Mr. G here today to talk about something that's rather undervalued in early years physics, and it's this idea of graphing or graphical representation. And I think it's a safe thing to say that there is no better way to represent your data in some sort of lab than with a solid and exact type of graphical representation. So you start learning about it quite young, at about the grade 7-8 level. However, we're really going to get into the nuts and bolts of it today to make sure that we all have a base understanding before we really start to dive into what these graphs can represent. So, first thing we're going to do is bring up the very basics of graphing. And first and foremost, you got to label the axes. I see far too often people having a single quadrant graph, and they just kind of leave the axis this way, the axis that way, and they're like, well, what do these mean? So, generally speaking, in science, the manipulated variable, or what we like to call the independent variable, the one that we control, that's always on the x-axis. So if we're the ones measuring the time, that is definitely going to be an independent variable. We are the ones that are measuring it. Conversely, the idea of the response variable, or the dependent variable, this is the one that is going to change as a result of our controlled variables. So with time, something is going to happen. With a change in distance, something is going to happen. Whatever is changing, that's going to be on our y-axis. So far too many people flip these up, and where that's going to hurt us is when we start to interpret the slope and what that might represent. So, big important thing. Second thing, make sure you give the graph an appropriate title. I love the people that just draw a graph and they figure that the graph is enough. Well, what are you graphing? Well, we have units and stuff like that. It doesn't matter. You have to title the graph. The most standard title involves the y variable versus the x variable, whatever that may be. Now, you can get into a discussion about, well, can't we just make a quick statement in the title and stuff like that? Yes and no. My experience says that just y versus x, whatever those variables are, is definitely a solid and easiest solution to that problem. The next one, and again, something that is well overlooked, is this idea of scaling the axes. Far too many people are given a full sheet of graph paper or a graphing grid, and they want to put the graph in like a small little condensed space. I don't understand why that is. We want our graph to be easier for us to draw, and when that's the case, you want to use as much of the graph paper as possible, or you want to use as much of the grid as possible. If you're given a square grid on something like a quiz or a lab or something like that, use the whole bloody thing, right? Don't just use a little corner. We're going to call you on it. I mean, put the title above it outside of the grid. The grid isn't necessary for something like a title, so make sure you use the entire grid. Choosing a scale. I mean, in this class, we're going to use a lot of computerized graphing, and when that's the case, it's going to choose the scale for us. However, we can also force feed the computer exactly what we want the scale to be. It's important for us to figure out a scale that makes sense and it's easy to read, so that we're not sitting there trying to figure out, well, you know, if that block is 0.12, then that must mean this and that. I mean, you want a scale to be a nice number that makes sense. So typically speaking, factors of 1, 2, 5, and 10, those are the ones that work the best. So something like a 0.2 per block or a 1 per block is ideal. These are really what we're looking for. So make sure you choose a proper scale. Finally, when you plot the points, it's super important that you don't connect the dots, okay? Your computer naturally is going to want to connect the dots. You don't want to do that because our graphs are not this violent market-looking type graph. It's going to inevitably be some sort of relationship, whether it be direct or inverse or square or some sort of other exponential power. It's not going to be this rigid sort of thing. So we got to make sure that we use, I mean, the most typical sense is the best fit line or best fit curve, but it's going to be something smooth. It's going to be something that is not volatile looking. So please, no connecting the dots. So let's take a look at a direct relationship. This is the most basic type of graph. You've all been dealing with this for years, and it looks something like this. It's a line. When we talk about a line, the most basic format of a line is the slope-intercept, and that's this idea of y equals mx plus b. And with mx plus b, our m, of course, is equal to our slope, and our b is equal to our y-intercept. Now, when we are plotting our data, we got to make sure that we fit the best fit line through the most points that we can, and even weight above and below. So the number of points above the line should be about the same as the number of points below the line. We're all going to possibly end up with a slightly different best fit line based upon our eye and our judgment of where the points are. Computers generally give you roughly the same best fit line every time. But if you end up with a best fit line with a different equation than other people, don't panic. You just chose something a little different. Just make sure you can justify it later. In general, slope is considered rise over run. You've dealt with this for years. If we start talking about it in terms of points, if we pick this point here and we pick that point there, we call this x2 comma y2, and we call this one x1 comma y1. Then we simply take these points, we plug it into this equation right there, you get your slope every time. For those of you that are a little more technical about it, keep in mind that we're really just dealing with something that is a right angled triangle. So rise over run, right? We're finding this distance here, we're finding that distance there. So whatever works for you is fine for me. I suggest not memorizing the equation. You got to know what you're talking about when you're dealing with it. So please make sure. Notice on this graph again, we didn't label some. I would say this is the y-axis, this is the x-axis. Always put it at the end. If it's going to continue, make sure you got arrows at the end, right? Very, very basic stuff. This is a single quadrant type graph. So when you're going to find the slope of the straight line, again, we've already shown you what you need. You need 2 points on the best fit line. So super important thing to note is that you only use a point on the line. Far too many people will fit the best fit line on their data and then choose their data points as the points they're going to use for the slope. Remember, we fit this best fit line because we believe that is the trend that represents the data that we've plotted, which means we want everything to be based upon an equation based upon that line. So make sure you choose 2 points on that line. Generally, we want them as far apart as we can. That doesn't mean pick the endpoints. It just means don't pick the points right next to each other. When I'm looking at a grid, I tend to look for the points that are actually on a nice whole box. You know, I don't want it kind of halfway where I have to guesstimate again and you get into all this idea of precision and accuracy and yada yada. So make sure you're only using the points on the line. Okay? Now, again, I'm going to come back to the idea that the equation for a line is y equals mx plus b. So you, with 2 points, are able to find the slope of the line, but with either one of those 2 points, you can also find the y-intercept. Now, we are going to be able to force feed what the y-intercept is. However, if we choose a best fit line and that y-intercept doesn't cross through, say, t equals 0, because we would expect time to be equal to 0, that's going to give us a clue as to the amount of error or even the human error that's associated with this particular calculation. So again, if you can be certain that the y-intercept is 0, well then of course you can plot that as a point, but still the best fit line may not necessarily go through there, so be careful. So let's take a look. We have this equation right here. Volt versus current for a simple circuit. You either know it or you don't. Really doesn't matter at this point. It's a graph. And we're going to determine the slope and y-intercept of the graph shown and write the equation describing the line. So, first step, we're going to find the slope. Now, in order to find the slope, we know that this is y2 minus y1 over x2 minus x1. We need 2 points. Well, let's take a look. This point right here is pretty much right through a crosshair. That's perfect. And I'm going to take a look at this point right here. It kind of looks to be the same. Again, notice how I'm saying it looks to be. It may not necessarily be. We can talk about that again when we deal with error analysis with our lab. So if we read this graph, we can see that, okay, well, this is 0.2, this is 0.1, and we have 1, 2, 3, 4, 5 blocks in between, which means each block must be worth what? Well, we went up by 0.1, and we divide by 5, and we get 0.02. That means each one of these little boxes is equal to 0.02, whatever the units are on the x-axis. So that's great. So if we're at 0.2, subtract 0.02, that means we're at 0.18 for our x. Now our y, you'll notice that instead of going up by 0.1, we're going up by 0.2, which means this is 0.2 divided by 5, which equals 0.04 per box, which means we're looking at, again, 0.4, which means if we read this one correctly, we should get 0.38, comma and 1 up from that, so 0.84. Okay, we have our 2 points. Now we just plug them in. So 0.84 subtract 0.4, and we're going to divide by 0.38 subtract 0.18. Now, for those of you using calculators, graphing calculators, all that jazz, I would throw brackets around each and every one of those. I can't tell you how many times people forget that, yes, even in grade 11, bed mass matters. So you got to make sure that all the stuff in the numerator is divided by all the stuff in the denominator. And if you've done it right, you should end up with a value of 2.2. Now, we don't know what the units are for these axes, so for now we'll leave it as is. But if we had units, we would put those at the end of the number. And that would help us along the way in interpreting our results. So number 2, we found the slope. We need to find the y-intercept. Now, the y-intercept is super easy. Why? Because we plug in 1 point. Now, there's really 2 schools of thought behind this. I'm going to use the second thought that I have. The first thought is, well, let's pick another point on the line, and then we plug it in, and we'll get our y-intercept, and life will be good. But we know that one of these 2 points that we selected to find our slope is definitely on our best fit line. So let's select one of those points instead and use it. So I'm going to use 0.18 comma 0.4. And how are we going to do that? Well, we know that y equals mx plus b. Okay, b is our y-intercept, so we want to solve for b. b is equal to y minus mx. Let's plug in our point now. The y value was 0.4, our slope was 2.2, and our x value is 0.18. And again, if we've done this all correctly, you should end up with a value of 0.004. Well, there we go. We have our y-intercept, we have our slope. There's our slope, there's our y-intercept, which means our equation is y equals 2.2x plus 0.004. Now again, like I say, if we were expecting it to cross through 0, 0, you notice that there's no point graph there because you can't really measure that. But again, it's one of those assumed points. If you want to use that, you know, that's something to talk about in your lab analysis. But again, you have to go with the data. You're going to have to explain out why the y-intercept is there, and if that's even within the error bounds. Again, we don't have any labels for the axes, but this is y and that's x. Again, that's not going to be the case once you figure out what current and voltage actually are and what the symbols are, but we're going to save that for grade 12. So, this is pretty much the method you use for any type of direct relationship. With a curved relationship, well, now you're going to get into discussions of whether you should leave it curved or if you should straighten the graph by either analytical means or using logarithms or any other different type of mathematical means. So that'll be another discussion for another day. For now, you have the basics to be able to do any type of direct relationship graphing. Best of luck to you. We'll talk to you again.